okay? Pressure, temperature, and in this case, volume. One of each variable. Which law is that? That's ideal gas. It is not combined gas law. It's not Boyle's law because it's not two pressures and two temperatures and two volumes and so forth. So it is ideal gas law. But I want to show you, because I think you all kind of probably picked up that's the ideal gas law. What would you have been solving for? N moles of what though? Why carbon dioxide?
It's the only gas.
It's the gas, right? And this is a gas law. So then if you got carbon dioxide in moles, and the question says to get to grams of calcium carbonate, what would you have to do?
Mole ratio.
Mole ratio back, okay, and then molar mass, right? I'm going to show you a trick. Whenever you have something at the same conditions, aka the same temperature and pressure, you can use something, actually I think later on we'll do liter ratios. They're just like mole ratios, but you just leave it in liters. Another trick, what conditions are present here? What are these conditions? Oh, actually, no, it's 298. That's not 0 degrees Celsius. Never mind. I was going to say, if this was STP, we would be able to use that lovely ratio, that lovely conversion with molar volume. Do you remember that? 22.4 liters per mole? Yeah, okay. If that was at 0 degrees Celsius, 273 Kelvin, we could actually do that. And I'll show you, I'll model that for you in a second. So, whenever you guys get PV equals nRT, what did you get for N? And this is moles of carbon dioxide, so 0.14, 141 moles of CO2, okay? And I'm guessing you got 1 atmosphere or 298 Kelvin, and that's already in liters, so everything is already appropriate. The R value is 0.0821 atmosphere liters per mole K. So then here, that's when you incorporate your stoichiometry. So it's a 1-to-1 mole ratio because it's already balanced. So 1 mole of calcium carbonate for every 1 mole of CO2, and so the moles of CO2 cancel. And then your last step is to go to molar mass. So it's like 100 grams, or is it 110 grams? 100.09. 100.09. That's what you're saying. Grams of calcium carbonate, just by adding it up from the periodic table, per 1 mole of calcium carbonate. And then what do you guys get for your grams of calcium carbonate? 100.09. There we go. What do you guys get?
I got 14.1.
So I was going to say 14 grams should be, 1.0 atmospheres should be our final 2 to 6 degrees. Yeah. So I used ideal gas law, and I rearranged this to be, because basically you're given T, P, and L, or volume. So if you know everything but N, then we rearrange to N is equal to PV over RT, and plug those variables in. I'm just not showing the plugging in. You guys can plug. Okay, I want to pretend this is at STP. Okay, just to give you another trick. If this were at STP, this would be 273 Kelvin, right? And this is where we don't have to actually use the ideal gas law. We can use the 22.4 liters per mole. So once you see this right here, 3.45 liters, that's my given. And I know I've got all this other given stuff, but that's just STP. So what was it, 3.45 liters of CO2? My goal is to get from CO2 to calcium carbonate. So I can actually go straight to moles of CO2 if this were at STP. The way I do it is just put 22.4 liters on bottom, 1 mole of carbon dioxide on top. And then the liters would cancel. Not even do an ideal gas law, I'm already to moles of CO2. And then the rest of it, you just proceed just like normal. Your calcium carbonate, 1 mole of calcium carbonate here, 1 mole of CO2 on bottom, and then the last step, the same exact step, 100.09 grams per 1 mole of calcium carbonate. And you would get the same answer. Actually, you wouldn't get the exact same answer because I've changed the conditions, but if it were at STP, basically I give you volume, you can go straight to moles. Does that make sense? This is old stuff. This is like stuff we did last unit though. Yeah. If it's at STP, you can go straight here. But this other one just had a different temperature, that's all. So it allows you to go straight there. Okay? Look at the second one and tell me, let's actually look at this one together, because this is the one I was going to show you the trick on. You have ethylene burning, blah, blah, blah. How many liters of water can be formed from 1.25 liters of ethylene, or sorry, if that much ethylene is consumed in the reaction? So, this is what I was telling you. If you have things that are at the same conditions, and the conditions are 1 atmosphere, 298 Kelvin, you actually can go liter to liter ratio just like you do mole to mole ratio. And I'll show you how it actually ends up being easier versus over, having like 7 steps in the front versus 3. So what do you want to start with here? If I want to just go straight stoichiometry. Great, let's start with the liters. 1.25 liters of ethylene gas, C2H4. Okay. What's your natural inclination right now? What do you think your next step should be? Go to moles, right? Okay, how would you go to moles from liters? Right, and I'm just going to tell us right now, let's just assume STP just for these tricks I'm trying to show you. If we assume that, then that's the only time you're allowed to use 22.4 because it's at STP. Okay? And so we got some moles. Then what would be your next step? If you're looking for how many liters of water can be formed. Mole ratio to water, right? So then water is a 2-to-1 ratio. 1 mole of the ethylene stuff on the bottom, 2 moles of water on top. And then the unit of the question is what? Liters. So then what would you do next? Right, at STP, that's the only time you're allowed to use 22.4. So 1 mole of water vapor would be 22.4 liters, right? And that's just because we're assuming STP. But what do you notice in the math? Can you simplify? You see the 22.4 liters here, and you see the 22.4 liters here. So we actually have this step and this step, which cancel each other out, which means that that whole mole ratio thing we've been doing, you can use liter ratios the same exact way using the coefficients, because these liters will always cancel out, so it'll always work out for us. So if I did see that cancellation, I can go ahead and look. What's really the only change I did mathematically? Times by 2, which is just the ratio that I'm looking for. So the way I would say would be also appropriate. You can do it that way, but it's not that hard. You can just cancel out your units and then go from there. This is the same thing. 2.5 liters of this guy times liter ratio 2-to-1. 2 liters of water are created for every 1 liter of ethylene burned. Right, but you see the math is the same. But I did in 1 step versus 4. Yeah. Because that's the conversion that's appropriate at STP. So if I went to moles, I had to use the 22.4 liters to get to moles. And then if I wanted to get out of moles, over here, to get out of it, I had to use the same conversion, but I flipped it. And so that's what I'm saying. It's redundant to do it that way. If you like this, you can go use liter ratios. It's just another trick for you. Another tool in your toolbox. All right, then you guys work on the last one. Do not, oh, darn it doesn't move. Hold on. You guys can calculate that if you need to. Go ahead and look at this one and do use the conditions given to you in the problem. Okay, the conditions were 298 Kelvin and 1 atmosphere. And I'm still checking homework. then the last one. There. Okay. Never mind. All right, where'd you guys start at here? Go for it, Hayden. Okay, well, did you start by writing down your givens? I'm just a quick reminder. We knew that was 1 atmosphere. We knew it was 298 Kelvin. We knew our question was volume, and we know that we have 75 grams of this stuff here. Okay, you said you want to start with that. Why? Right, convert that to moles and do what with it? But this one I told you to go back to the original conditions, which are not STP. But you are supposed to go to moles. Why do we have to go to moles of this? Is that in? Not quite yet. So tell me, what's the molar mass of this? What's the molar mass of that? 167.8? 836, okay. Grams. So that's the C2H2Cl4. Okay, and this is getting us close to N, but we're not to N yet because the question was regarding chlorine gas, right? So our N has to be in reference to chlorine, not this acetylene. Oh, this is acetylene gas. This is acetylene gas. That's what blew the pumpkin's face out. There we go. Okay, so what do you want to do next? Mole ratio. Thank you for what goes on top though. 2 for chlorine, thank you. Some of us are like, we are running the class. Okay, there's one of these, there's 2 of these, so 1 mole of the C2H4Cl4 goes on bottom. So this is going to give us N of chlorine gas. My people who have done it, what is it? What is that? Yeah, Zachary.
0.8.
0.894. 0.894. Is that what you said? Okay, that's N, that's P, that's V. That's T, we're looking for V. What law are we using? Ideal gas, right? You will love the ideal gas because it will help you every day. V is equal to nRT over P. And then everything is an appropriate unit form. So plug in 0.894 times 0.0821 times 228. All that divided by 1. Oh my goodness. I cannot believe I just put divided by 1 on my calculator.
Yeah.
I know. I just did. 21.8 liters? Yeah, 87 liters, so it'd actually be 21.9, if anything. Actually, 22 liters if we're going with 6 jigs. There we go. Okay, do me a favor. Look at, actually no, let's talk about Graham's law first, and then we'll look at problem set 14, because I got a couple more people that I need to check. But problem set 14 should be like mostly done. When I say mostly done, there might be 2 Graham's law problems you do not know how to do. But you know how to do everything else, and you've had it for quite a few days, so make sure you're making progress on that, because it should be done by the end of today, but we'll see where we are. Can I go ahead and pull up Graham's law notes? Anybody else still looking here? Okay, I've got just a 1 slide of like the background, and then there's 2 problems I want to practice with you, and that's it. So take out some place you're going to be writing down Graham's law information. And so problems like we just did for warm-up, you will have like probably 2 of those in your test. Okay? Cool. Let's look at Graham's law. So guess who gave him over this one, guys? Mr. Graham. Somebody named Mr. Graham. And it basically talks a little bit about what we mentioned yesterday with how fast things move. I mean, how fast certain weighted molecules move. So heavy things move quick or slow? Slow. Small things move fast. And so that's basically what this is kind of getting at. There's a formula for it, though, okay? So tell me what a fusion is again. And I'll draw a balloon to remind you of that. Okay, so the, what's the word I'm looking for? Gas escaping through a small hole, and it's still moving like in the same direction that diffusion moves. It's moving from high concentration to low concentration. Concentration, brackets mean concentration, by the way. Brackets mean concentration. So it's always moving from high to low. So there's a lot of gas particles in here. Let's call it helium, because that's a lot of times what's in a balloon. It's going to be moving out through the small opening. So what if you had helium, carbon dioxide, and water vapor in that balloon? Let's say you had all three of those gases. Which would be the predominant one that's left over after they've had time to escape? Maybe here, let's go this way. Who's the first to leave? Why helium? Super light. It's going to be out of there in no time. Who's next to leave? Why water? Right, it's 18 grams per mole. It's the next lightest. And then CO2 would be the last to leave. But they're not like waiting in line to leave, right? They're all leaving at the same time, out of that hole. But helium's going to be removing itself way faster than any of the other ones. So the predominant one would be carbon dioxide left over. So you kind of got the concept already. Yeah.
What did you say that age?
High concentration to low concentration. So from inside the balloon to outside the balloon. Okay, so basically though, because that inverse relationship, heavy things move really slow, we call it an inverse relationship. So the rate of diffusion of any gas is inversely proportional to the square root of its molar mass. So that means the speed of the gas is equal to the square root of 1 over its molar mass. That's one version of Graham's law. But most of the time in Graham's law, we're comparing things. Like we just compared three gases just collectively together. A lot of times you're not looking at it as a singleton. So I'm going to show you how we actually express it in a comparison form. So let's say this is speed of gas A, and this is molar mass of gas A. So Graham's law, and you have this in your foldable already, is rate of effusion of A over rate of effusion of B, these are two different gases, is equal to the square root of the inverse of their molar masses. So what's going to go on the bottom, A or B? A, because it's the inverse, molar mass of A, and then B is on the bottom over here, so it's the inverse, so it's going to be on the top of the fraction on this side. That's it. And so you know that lighter things move faster, and so to make the rate like a quantity that actually makes sense, I always tell everybody to put if you know the gases, put the lighter one on top, okay? And that will make your math easy. That'll make your math make more sense. Because if you're saying, oh yeah, helium gas moves 4 times faster than water, versus water moves 0.25 times faster than helium, which makes more sense? First one, because you understand like things that are in multiples versus in fractions. Okay, so let's go ahead and do a problem with these. So tell me the relative rate of diffusion or relative velocity, is talking about speed, of hydrogen versus carbon dioxide. Okay, so we know our general equation, which is what? Okay, so Ray, I want you to tell me who A and B are there. Why is hydrogen A? Okay, it's lighter one, so this one's going to be A, and that's going to be H2 gas, and then B, CO2. Okay, so what do I put in the square root? What goes on top? Where are you getting 44 from? Molar mass of carbon dioxide, right? So carbon is 12 plus 16 is 44.01 grams per mole, because that's its units, its molar mass, over what? 2.016 grams per mole for hydrogen gas, because it's hydrogen plus hydrogen. And then you'll notice that the grams per mole, they cancel each other out, so we're just stuck with a number. No unit, just a number. Everybody pull out your calculators, give me that number. Sodium. Stop there. Okay, cool. So, this number, 4.67, what does that mean? I want you to put it in a sentence. Go for it, Gwen. Perfect. Hydrogen moves 4.67 times faster than CO2. That's it. Grams law is pretty easy. It's just you gotta know your formula. And remember they're inverted, okay? So I give you two gases, known gases, and you had to find the rate of diffusion, the comparative rate of diffusion. I could give you the rate of diffusion, their comparative one. I give you one gas, and your job is to find the other gas. Well, how would you find the other gas? Based off what information? Molar mass. I heard somebody say it. Thank you. You're going to look at the molar mass law. So that's our next example. An unknown elemental gas. So when it says elemental gas, it means it's a gas straight from the periodic table of elements. Okay, so it's from the PTOE. It fuses 4.5 times faster than krypton gas. What is the molar mass of the gas, and then what's the identity? Okay, so take a second. Think about who is faster here, krypton gas or unknown gas? Unknown gas. So is that going to be A or B? A. Okay, so rate of unknown gas over what? Rate of krypton, okay, equals square root, what goes on top of in this fraction. What's krypton's mass? Periodic table. It's like 80 something? 83.8. 83.8 grams per mole. Okay, so krypton's on top. What goes on bottom? No, not quite. It's the molar mass of the unknown. Do we know it? No. So just put X. Okay, we're going to solve for X. But what Lizzie said, all of this equals, so the rate of unknown over rate of krypton equals what? 4.5 times. Okay. So really what are we looking at? We're looking at the square root of this over X equals 4.5. How do we mathematically solve this? Square everything. That's a 2. Okay, so then we get 83.8 over X equals, what's that squared?
4.5.
Yeah, what is that squared? Oh, 20, okay, 20.25. Okay, then how do I solve for X? Huh?
Multiply by 83.8.
No. Let's go baby steps, guys. I need to switch things, right? So I need to multiply by X on both sides.
So you divide by 82.8 times 20.
Right. So the X cancels out on this side, so you get 20.25X. So then to isolate X again, you have to divide by 20.25. Don't just try to do it in your head. You can write it out. So what is 83.0 or 80 divided by 20.25?
4.138.
So X is 4.138 grams per mole. So we got the molar mass of the gas. Who is it? Who is it? Helium. Helium weighs approximately 4 grams per mole. All right, and that makes sense because it's lighter and it's moving a lot faster than krypton. If you find a molar mass, let's say molar mass of 28, no, let's say molar mass of, I don't know, 39. Molar mass of 39. Who would you guess? So you guess potassium up front. You're like, oh, that's the molar mass of potassium. But is potassium a gas? No. So you have to kind of have that second filter of like, oh, that's not even a gas. It can't be potassium. So then what would be the closest one? Argon. Okay? So don't forget your brains. They're there. Okay? So let's stop this for now. We got Graham's law kind of taken care of. Keep your problem set on your desk for me. Pull out a piece of paper. Label it molar mass of butane lab. Molar mass of butane. We're going to watch a quick video on how to do this lab. And then you guys will do it. molar mass of butane. It's pretty interesting. It's a cool lab. You get to play with lighters too. But they don't light, okay? The lighters don't light. You know, like the little big flick lighters? Okay, they don't light. Because I took the flint out. Because we didn't want Mr. Smith when we have fire. So, I will advise you, whenever you flick you pull it back, it's going to start letting the butane out like crazy, and you don't know it. So just don't do it until you're ready to. Okay, so I'm going to let you watch this quick video this lady put together. It tells you exactly how to do everything, because you'll have error if not. And from there, let's just roll. So let me show you this first. Let me just take this down, and watch. I saw. I'm going to speak for it. All right, so you got your stuff. You will first have to mask the lighter. Okay, when you mask the lighter, you have to dunk it in water first, because if you're going to be putting it underwater in the end, so it needs to have the same conditions. So you just drop it in water, and then you shake it off, and you mask it a little, or dry it off a little bit, not a whole lot. And then from there, after you mask it, you're going to fill the graduated cylinder that you'll be using all the way to the top. So you're going to have to probably get a beaker and pour it. It's water, yes. And so she's going to pour it in the graduated cylinder all the way to the top. So if there's a gap, so you can see there's a gap right there, you're going to have to redo it. Because if not, because that's going to count as volume of a gas if there's a gap, and that's going to skew your results. So then you want to make sure you pour it all the way to the top, and then you put your hand on it. So you see how she's got it in her hand. You're going to cap it, squeeze it pretty good, and then you're going to flip it over and underneath, so the graduated cylinder is upside down and there's a huge water column inside. And so you just have to make sure that you do it so that there's no gap of air. So if there's bubbles in it, you have to retry, let all the water out, try again. So that's probably one of the hardest parts. Then you're going to put the Bic lighter underneath the graduated cylinder's mouth, which is way deep down below the water surface. And so underneath water, you guys see that? Underneath the water, that's when you're gonna pull the trigger. You can see the bubbles. You see the bubbles? That's what you're gonna do. And then it's going, in my lab sheet, it says fill it with bubbles all the way until the gas comes all the way down here, until it's even with the water level on the outside. Okay? Sweet bubbles. Okay, so oops, I don't have my marker on. In y'all's lab, it says to fill all the way to the line, to the level of water outside. And then after that, you guys have some other variables you're going to be measuring. But that's just the general setup I just wanted to show you. There are a couple pieces of data that I will give you. Go ahead and write them down now, right here. Write that down for yourself. Because dealing with stuff, collecting gas with water vapor kicks up really, really easily. So there's water vapor already present. So we're going to have to also look at the water vapor pressure, P of water. We're going to look at that up on this link here. I also have a huge book like this big full of values. Nobody wants to look through, so I'll pull it up right here for you. But a lot of that's detailed out in your lab itself. So this is the P total. This is P atmosphere. This is in inches of mercury, though. What do you think you're going to do with that? Do you know how to convert to millimeters? Okay, so you know how to convert from inches to centimeters and then from centimeters to millimeters. And that's because we're in America and we deal with inches. Other than that, just a tip if you need it. P total, which is all the gas you have total in the atmosphere, is equal to our gas of interest plus the water vapor. That's whose law? We talked about him yesterday. Dalton's law. Right. Okay. So you guys get into groups of 3 called the molar mass of butane lab. You'll find it in your lab notebooks, and I will help you as you need to set up. But it's a really easy lab to set up, okay? Okay. You'll be able to do it. Okay. Grams log? On the PS14? I think there's one on there. I'll have to check.